Welcome back to Physical Science 101. This time we're going to apply the energy principle that I introduced to you last time. So let's take a look at the energy principle again. Once again, we have this box that represents the energy in an object, and that object can have kinetic energy or potential energy inside of itself. And we can add energy by doing positive work, or we can take away energy by doing negative work. Now, even if we don't do work, the kinetic energy can increase or decrease if we have a corresponding increase or decrease in potential energy. So bringing that all together into one equation, the energy principle equation says that any energy increase has to equal the work done plus any corresponding energy decrease. Or in other words, an energy increase has to either come from work, or it has to come from an energy decrease, or possibly both. So the energy increase equals the work plus the energy decrease. That's our energy principle. That's what we're going to be using. Okay, let's do an exercise. Okay, so here's a question that applies the energy principle. How much work is done in raising a 10-kilogram backpack from the floor to a shelf 1.5 meters above the floor? Now I'm just going to work this one first so that you can see how we apply the energy principle. We'll start with the floor. There's the backpack. The mass is 10 kilograms, and its height is equal to 0 meters. And then we raise it up to a shelf. So there's a backpack on the shelf, and its height is now 1.5 meters. Now, also important is that the backpack is not moving while it's on the floor. So its speed is 0 meters per second. And when we put it on the shelf, its speed is still 0 meters per second. So that is a diagram of the statement. Now let's look at the energy. Let's do an energy diagram. Okay. So in the box, as we go from the floor to the shelf, the potential energy increases. Potential energy increases as we go from the floor to the shelf. The kinetic energy is 0 to begin with and 0 at the end because the backpack is not moving when it's on the floor. It's not moving when it's on the shelf, so the kinetic energy stays the same. So we have an increase in potential energy, no change in kinetic energy. And the way that the potential energy increased is that we have some work being done. So that is our energy diagram for this situation. We have potential energy increasing, kinetic energy staying the same, and work being done. So now we apply our energy principle, and our energy principle says energy increase equals the work done plus any energy decrease. Okay. The energy increase is the potential energy. That is what increased, potential energy increase. So the potential energy is the increase. That's equal to the work done plus the energy decrease. Well, we don't have any energy decrease, so we have nothing for energy decrease. We can just scratch that out. Okay, we have an increase in potential energy and we have work. So that is how we apply our energy principle. The increase in potential energy equals the work done. Energy increase equals work plus energy decrease, but we have no energy decrease. So what is the potential energy? What did the potential energy increase by? Well, it increased to mass times g times height, where mass is 10 kilograms, g is 9.81 newtons of weight per kilogram of mass, times a height of 1.5 meters, and that is equal to our work. So let's do our calculation. We have 10 times 9.81 times 1.5, and our number is 147. That is the increase in potential energy. What's our units? Our kilograms cancel out. I have newtons times meters, so that's a joule. And that is equal to the work. That's what we were asked to find. So the work done to move that backpack from the floor to the shelf was 147 joules of work. So that's how we do an energy, that's how we answer a question using the energy principle. We draw a diagram, and then we do an energy diagram showing what energy increased, what stayed the same, whether there was any work done, and we use our energy principle. Energy increase is work plus energy decrease. In this case, the energy increase was potential energy. We had some work, so we had to calculate the potential energy of the backpack on the shelf, which was m times g times height, or mass times g times height. We did that, and we found out that it took, someone had to do 147 joules of work to get the backpack from the floor to the shelf. Okay, another question that applies the energy principle. How much work is done in stopping a 1,000 kilogram car that is moving straight down the highway at 17 meters per second? Now this time, I would like you to try, okay? Draw a diagram of the situation, do an energy diagram, and see what you can do. And so pause, try that, and then come back and I will work through it. Okay, let's draw a diagram of what's happening. Here's the car, and its speed is 17 meters per second, and it's on the highway. And we're going to say its height is 0 to begin with. And in the end, its speed is equal to 0, but its height is still equal to 0. So it moves that way. And the mass of the car is 1,000 kilograms. Okay, so we have a 1,000 kilogram car moving at 17 meters per second, moving straight down the highway. It comes to a stop, so 17 meters per second to 0, and its height is 0 to begin with and 0 to end with. So that's a kind of a picture of what's going on. Let's look at the energy situation. Do the energy situation. Well, what's going on here? The car has kinetic energy here, and it goes to 0, so our kinetic energy is decreasing while our potential energy stays the same. The height is 0, the height is 0, stays the same. And so if the kinetic energy is decreasing and the potential energy stays the same, there must be some negative work, some work taking energy out of that object. So we'll apply our energy principle. Energy increase equals work plus energy decrease okay? Energy increase is 0. So energy increase is 0, nothing increased. And then we have work That's what we're looking for, plus the energy decrease. The energy decrease is kinetic energy. Okay, so that's our equation. I'm looking for work. I want to get work by itself, so I'm going to subtract off kinetic energy from both sides. Okay, so I have minus kinetic energy is equal to the work done. So it'd be minus 1/2 mv squared, that's my kinetic energy, is the work done. So it'd be minus 1/2 the mass of 1,000 kilograms times the speed of 17 meters per second. That is the work done. We'll do some calculations. 1/2, or minus 1/2 times 1,000 times 17. Oops, I forgot my squared. 17 squared. So minus 1/2 of 1,000 times 17 squared equals minus 144,500 joules is the work done. And why is it negative? It's negative because something took energy away from that car. The car had kinetic energy to begin with, and then it didn't. And that kinetic energy didn't go into potential energy, so something must have taken that energy away. The car had a net decrease in energy. So it went from having kinetic energy to having no kinetic energy because something did work. Something applied a force opposite the motion. Something did a force opposite the motion to bring that car to rest. Something did negative work on that car. So, and the amount of negative work was minus 144,500 joules of work. Okay, another question. A force of 200 newtons is needed to push a table across a level classroom floor for a distance of 3 meters. How much work did this force do on the table? So that's one question. How much work did the force do? But then the second question is, if the table starts from rest and stops at rest, how much work did friction do on the table? So first off, how much work did the applied force do to the table? And the second question, how much work did friction do on the table? Remember, the table starts from rest, stops from rest at the same height. So try that, work with that, see what you can do, pause, and then come back when you're ready to see me work through this. Okay, there's the floor, here's the table, and there it is across the floor. Let's see, the distance is 3 meters. It starts from rest. It ends at rest. It's at 0 height to begin with, at 0 height to end. So the table is pushed a distance of 3 meters, starts from rest, stops at rest, no change in height. Okay, and then there was an applied force. And the first question is, how much work did that force do? Well, actually, we know what the force is. Force is 200 newtons. So the work of the force is simply the force times the distance. So work is force times distance. So the work is the force, 200 newtons, times 3 meters. So that would be 3 times 200, 600 joules of work done by the force to push that table across. Okay, so that we can do, and it's positive. It's positive work because the force is in the same direction as the motion. Now, to answer the question of how much work did friction do, we have to consider the energy principle. Okay, so for that, let's draw our energy diagram. Okay, we did some work on the table, but the kinetic energy did not change. The table was at rest and the table wound up at rest. So kinetic energy was constant, didn't change, and neither did the potential energy change. It was at zero height to begin with, zero height at the end. So the potential energy also didn't change. So work put energy in, we put in 600 joules of energy. We put in 600 joules of energy in, but then there was no change in the energy of the table, so that energy must have gone right out of the box in the work done by friction. So we put in energy, the box, or the table didn't change its energy, so that energy went out by friction doing work. So we do our energy principle, energy increase is equal to the work plus the energy decrease Okay, energy increase is 0. Work is our 600 joules plus the work done by friction. So that's the work that was done. Our work and friction's work. Nothing decreased, so 0. So we have 0 is equal to 600 joules plus the work done by friction. We want to get the work done by friction by itself, so I'll subtract 600 joules from this side and 600 joules from that side. Sorry, it's a plus. So minus 600 joules, those cancel out, is equal to the work done by friction. Okay? So the friction did just as much negative work as we did positive work because the energy that we put in went right out to friction. So the table didn't gain any energy at all. Our work went right out to friction. So the work done by friction is negative 600 joules. It's negative because as the table moves this way, the friction force is opposing it. So friction did negative work on the table and took away all the energy that we put in. So we put energy in and the friction took it back out. Okay, here we have another variation on the theme of the energy principle. If a 2 kilogram book falls off of a shelf that is 2 meters above the floor, how much kinetic energy will the book have as it hits the floor? So no work is done on the book. Now, this is not after the book has come to rest. We're asking for the kinetic energy as the book hits the floor. So think just before the book hits the floor. It is moving. The book is moving just before it hits the floor. So if it's moving, it has kinetic energy. So the book has kinetic energy as it hits the floor. So we're not talking about once the book comes to rest. We're talking about while the book is still moving, as it hits the floor, how much kinetic energy does it have? So once again, think energy principle and think no work being done and see what you can do with this. Okay, here's the book. It's on the shelf, so it starts off with a height of 2 meters, and on the shelf its speed is 0. So it's 2 meters above the floor. Its mass is 2 kilograms. So mass of 2 kilograms, 2 meters above the floor, no kinetic energy. It falls off the shelf. The floor, its height is equal to 0. Its speed is not 0 as it's hitting the floor. And that's all we need. Okay, and no work is done. We're told that no work is done. So 0 work. Okay, that's everything. Now let's think about our energy diagram. Our energy diagram has potential energy decreasing. It's going from 2 meters to the floor, so potential energy is decreasing, but it's speeding up. It's not moving to begin with, and it is moving at the end, so kinetic energy increases. No work's being done, so we don't have any arrows going in, so we can see that that increase in kinetic energy must have come from that decrease in potential energy. Let's put that in our energy principle. Our energy increase is equal to our work plus our energy decrease. Our energy increase is our kinetic energy. That's what we're looking for. Is equal to our work, which is 0, plus our energy decrease, and our energy decrease is our potential energy. All right, so there we go. Kinetic energy is equal to our potential energy, which is mass times g times height. Our kinetic energy is 2 kilograms of mass, 9.81 newtons per kilogram of g, and a height of 2 meters. So the kinetic energy must be equal to 2 kilograms, or 2 times 9.81 times 2. That would be 39.2. And once again, our kilograms cancel out. Newtons times meters, that's a joule. So as that book hits the floor, so as it falls and just before it hits the floor, its potential energy has turned into kinetic energy, or its kinetic energy is increased while its potential energy is decreased. So its kinetic energy must be equal to the potential energy that it had on the shelf, which was 39.2 joules. Okay, here's a multiple choice question. The potential energy of a box on a shelf relative to the floor can be thought of as A, the work that was required to put the box on the shelf from the floor, B, the weight of the box times the distance above the floor, or C, the energy the box has because of its position above the floor, or D, all of the above. Okay, so once again, think about that. Think carefully, read through, think about it. Definitely come down on an answer. Don't just wait to see the answer. Think and come down on an answer, and then I'll let you know what it is. Okay, so let's think about the potential energy of a box on a shelf. Well, we have potential energy is equal to mass times g times height. Well, first off, that is the energy of the box's height. So the potential energy is the energy that the box has because of its height. So that was C. But let's think about this. Mass times g, that is equal to the weight of the box. So potential energy is also the weight of the box times the height. So that was question B. So we have both C, because potential energy is the energy of the position, the height being the position, and we also have potential energy being the weight times the height. Now let's think about our energy diagram. as we lift the box from the floor to the shelf, our potential energy is increasing. Okay, so going from the floor to the shelf, potential energy increases. If the box is at rest on the floor and at rest on the shelf, kinetic energy stays the same. So that means that some work must be done to increase the total energy in the box. So if we look at our energy principle, energy increase is equal to work plus energy decrease, and we don't have any energy decrease, so I'm just going to put 0, and the energy increase is the potential energy, so the potential energy is also equal to the work done, and that was A. So in this case, A, B, and C are all true, so the correct answer is D, all of the above. Okay, another multiple choice question. Kinetic energy can be thought of as A, the work done on an object to put it in motion, B, the negative work done on a moving object to bring it to rest, C, both A and B, or D, neither A nor B. So think about it, and once again, think about it in terms of the energy principle. Think about it in terms of the energy principle, and come down on an answer, and then I will tell you what the answer is. Okay, so kinetic energy can be thought of as the work done on an object to put it in motion. Let's think about that. If we put an object in motion, okay, so something is not moving and then it is moving, then its kinetic energy increases while its potential energy stays the same. So something must have done work to increase that kinetic energy. So we look at our energy diagram, energy increase is equal to the work plus energy decrease, but that's no energy decrease. So the energy increase is kinetic energy. So the kinetic energy is the work done to put the object in motion. So that is the object's kinetic energy, is the work done to put the object in motion. Now let's think about B, the negative work done on a moving object to bring it to rest. Well, that's the opposite situation. We have an object coming to rest, so its kinetic energy is decreasing while its potential energy stays the same. Well, if that energy decreases, if the kinetic energy decreases and potential energy doesn't increase, then there must be some negative work bringing that object to rest. So going through our energy principle, we have energy increase. Well, there's no energy increase. That must be equal to the work plus the energy decrease. Okay, so 0 is the work plus the energy decrease. The energy decrease is kinetic energy. Okay. So subtracting off work from both sides. So minus work is the kinetic energy. So once again, that's B. The kinetic energy of the object is minus the work done to bring it to rest. So A is true and B is true. So the correct answer is C, both A and B. Okay, another question. Two cars have the same mass, but one is moving 3 times as fast as the other is. How much more work will be needed to stop the faster car? A, the same amount. B, twice as much. C, 3 times as much. Or D, 9 times as much. Okay, once again, think about it. Definitely come down on an answer, and then I'll tell you. Okay, we have two cars. I'll call this one A, and I'll call this one B. And we have VA and VB is 3 times VA. So VB is 3 times VA. So the kinetic energy of A, 1/2 mVA squared. And for B, kinetic energy is 1/2 mVB squared. But VB is 3 times VA. So the kinetic energy is 1/2 the mass. Now I have to square both of these. I have to square the 3 to get 9. 3 squared is 9. VA squared. So the kinetic energy is 9 times 1/2 mVA squared. So the kinetic energy of B is 9 times 1/2 mVA squared, or 9 times the kinetic energy of car A. So the correct answer here is D, 9 times as much. 2 more questions. The first is, if 5,000 joules of work is used to raise a 102 kilogram crate to a shelf in a warehouse, how high was the crate raised? Or in other words, how high is the shelf? Once again, this is an energy principle question, so use your energy principle to answer this question. Okay, start with a diagram. We have a crate raised up to a shelf. The mass of the crate is 102 kilograms. And 500 joules of work was used. So the work is, 5,000 joules of work. Starts off on the floor with a height of 0, and it ends up with a height that we don't know. And the crate is not moving on the floor. Speed is 0. And when it's on the shelf, it's also not moving. Okay? So that's all the information in that question. The crate is not moving on the floor to begin with, and then it's not moving on the shelf to end with. It took 5,000 joules of work to lift that crate up, and the mass of the crate is 102 kilograms. Okay, so that's everything. Let's think about our energy now. Now that we have a picture of what's going on, let's think about energy. Okay, in the box we have potential energy increasing. It goes from here up higher, so that's an increase in potential energy. But our kinetic energy stays the same, no kinetic energy to no kinetic energy. And we had some work done, so that's where that potential energy came from. That potential energy came from the work of actually 5,000 joules. 5,000 joules of work was done to raise that crate. Okay, energy principle, energy increase is equal to the work plus the energy decrease. Nothing's decreasing, so I'm going to go ahead and put 0 for that. Okay, the energy increase is potential energy, so potential energy is equal to the work. Now I have something for either of these. Potential energy is mass times g times height, and the work is 5,000 joules. Okay, height is what I'm looking for. So when I get height by itself, I'm going to divide by mg, cancels out mass times g right there. So I have height is equal to 5,000 joules divided by a mass of 102 kilograms times a g of 9.81 newtons per kilogram. Okay, so my height is 5,000 divided by 102 times 9.81, where I put parentheses around 102 and 9.81. So make sure you put parentheses around all of that to divide by both of them. So 5,000 divided by 102 times 9.81, and I get 5 watts. Okay, let's look at my units. My kilograms cancel out. I have joules divided by newtons. Remember that a joule is a newton times a meter. So newton times a meter divided by newtons leaves me with 5.00 meters. So the height of the shelf is 5 meters. Okay, last question using our energy principle. A 1 kilogram ball is dropped from 9 meters above the ground. Using energy considerations only, find the speed of the ball just as it hits the ground. So once again, not when it's on the ground, but just as it hits the ground. So as the ball is falling, it is moving, and so just before it hits the ground, it is moving with some speed. Now this is something that we could have done in the last unit using force and motion, but this time I would like you to do it using energy considerations, using your energy principle. Okay, try, pause, and then come back when you're ready to see me work through it. Okay, here's the ball, falls down, and just before it hits the ground, so it has a height of 9.8 meters, and at the end its height is 0. The mass of the ball is 1 kilogram. So mass is 1 kilogram. The height to begin with, the initial height is 9 meters. Falls down, the height is equal to 0. It's dropped from rest, so V is equal to 0 to begin with. And the question is, what is its speed just before it hits the ground? Okay, that's the question. Let's do our energy box. Okay, as the ball falls, its potential energy is decreasing. And while its kinetic energy is increasing. So potential energy decreasing, kinetic energy is increasing. No, we weren't told about any work, so no work either in or out. So our energy principle is energy increase equals our work, no work, plus our energy decrease. So our energy increase is kinetic energy. Our energy decrease is potential energy. Okay, so the kinetic energy it has as it hits the ground is equal to the potential energy that it had up top. Okay, well, what can we do with that? Well, we know that kinetic energy is 1/2 mv squared. Potential energy is mg height. And look at this, we can divide both sides by mass, and that cancels out our mass, so actually mass doesn't matter. I didn't have to tell you that the mass was 1 kilogram. The same would be true for any mass. So what are we left with? We're left with 1/2 v squared is equal to g times height. Okay, I want to get v by itself, so I'm going to multiply by 2. Okay, 2 times 1/2 is 1. That cancels out. So I have v squared is equal to 2 times g times height, or v squared is 2 times 9.81 newtons per kilogram times a height of 9.8 meters. So v squared is 2 times 9.81 times 9.8, and that gives me 192. Now what are our units? So newtons per kilogram, let's look at that. So a newton per kilogram times a meter. So a meter times a newton per kilogram, that's equal to a meter times a kilogram, meter per second squared, divided by a kilogram. So that must be, my kilograms cancel out, that's meter squared per second squared, as it should be. So I have 192 meters squared per second squared. So my speed, to get my speed, I'll just take the square root of both of those. The square root of 192 is 13.9. 13.9, and the square root of meter squared is meters, the square root of second squared is seconds. So the speed as the ball hits the ground is 13.9 meters per second. And we can do that just by thinking about energy, because its kinetic energy must have come from its potential energy, so we can use that to find the speed of the ball. Okay, that's enough for now. So until next time, think science.